actually positive. Oh, sorry. All right, so um, this is going to be the first notes you take on related rates. So before we even start doing any actual word problems with them, that'll come in the next set of notes. I just want to get you used to the language and used to the formulas you need to know how to derive. So it's going to be pretty similar to what you were doing with implicit, where you would take the derivative of y cubed, but the variable of change was x. So we would say that's 3y squared times y's derivative, which is really dy dx. And when we did it with implicit, we called it y prime. When we do it with the word problems, we're going to want to use the formal notation. Couple things are going to change. First of all, in the real world problems, things don't change with respect to x, they change with respect to time. So we'll be taking all our derivatives with respect to time. It'll still work the same way. So if I did the y cubed with respect to time, I would still do 3y squared, but I'd multiply it by the rate of change of y with respect to time. So it becomes a dy dt instead of a dy dx, but it's very similar. So the first thing we're going to do is translate some sentences into calc notation, and then we'll go take the derivatives of all the geometry formulas you need to use. So if I were to tell you the area of a circle is increasing at a rate of 6 square inches per minute. The increasing tells me I have a positive growth. Rate tells me I have a derivative with respect to time. And the area tells me what to call my variable. So if I were to translate this into calculus, I would say the rate that the area is changing with respect to time, which I'll call dA dt, is equal to a positive 6 because it says it's increasing. If it said the area of the circle was decreasing, I'd use a negative 6. So a situation for this would be maybe when you toss a rock into a lake and you get these concentric circles. You can see that many things are changing at one time. The radius is changing, the area is changing. So that's why they call them related rates, because different things change in the same situation. Man, I'm warm. This is, oh. Sorry, I'm not starting over either. Anyway, so that would be a positive. Sometimes when I forget, I'm recording myself. All right, square inches per minute. Stop laughing. There's kids in here. All right. Anyway, the next one, very similar, we're going to translate this into a calculus related rate. The volume of a cone is decreasing. Maybe it's water in a cone, or maybe it's the cone itself, but maybe it's sprung a leak, and so its volume is going down. Well, its volume goes down, so does other stuff, like its surface area of the water, like the depth of the water, the radius of the water. All those things are decreasing at the same time, which is why we call them related rates of change. So I'll call my volume V. It's decreasing. That gives me the sign of my rate of change, and then it tells me how much. So if I translated this into calculus, I'd say the rate that the volume is changing with respect to time will be equal to a negative due to the word decreasing, and then I'd say 2 cubic feet per second. Labels are really important in these the word problems that we're going to be doing, so make sure labels get on all of them. I'd like you to pause the video and go try setting up number 3. So our first task is just, can you take a sentence and translate it into some calculus notation? So pause the video, go try number 3. So this is a height changing, I'll call that h, and it's the height of a tree. The tree's growing, so it's increasing at a rate of a ½ foot per year. So I would say the rate that the height is increasing with respect to time is equal to a positive 1/2, and that would be feet per year. So our first task is, can you translate a sentence that has a related rate into some calculus notation? Now we're going to go in reverse. Can you take a related rate and put the words or the sentence that would go with it? I'm not going to do all of these. I'll pick maybe number 5. So I don't know what A stands for, but if I go look at the label, right, I can see it's cubic feet per second. So I can see that that label is telling me that A is standing for acceleration. So notice how helpful the label was. My first gut instinct was to call A area, but then I looked at the label and I saw that it is feet cubed per second. Actually, that label wouldn't be acceleration, that'd be feet per second squared. So feet cubed would be like a volume changing over time, which is weird. They're calling it A. So again, deciphering this, I would say that the volume A, which is weird that they're calling it A, but whatever. I would have called that V if I had made these notes, but the volume A of, let's say, a whatever, let's say a box, is changing at a rate of -4 feet per second, or if I want to say is decreasing, I can absorb that negative with my word choice. So I either have to say it's changing at a rate of a -4 or it's decreasing by 4 feet cubed per second. What I can't do though is say it's changing at a negative rate of 4 because that gives me a double negative. So let's go look at maybe the one over here. Let's say R stands for radius. That would make sense because radii can be measured in centimeters and then per minute. So I would say the radius of what I don't know. It could be a cone, it could be a sphere, it could be a cylinder. It doesn't really matter. The radius is, all right, I can say changing at a rate of 4 centimeters per second, or I can say increasing because that's a positive. So I'm going to say is increasing at a rate of 40 centimeters every minute. Is this bugging you guys? Am I bugging you? Okay, awesome. So then, oh my God, I don't want to redo this video. Stop it. All right. Sorry, people are making me laugh, and I almost choked myself because I'm on a cord. All right. All right. I'm not starting this over. All right, so in the next thing we're going to have formulas that we're going to start off mostly with geometric formulas because that's what we know. But this process can be applied to a formula for anything that's changing over time. So this says to identify what formula this is first. Pi r squared is obviously the formula for the area of a circle. By the way, it's calculus that gives you all these formulas. You have to memorize them for now because it's what you've been told, but when you get in Calc 2, we actually tell you why the area of a circle is pi r squared, so you get to kind of see the value of calculus. It gives you all your geometry formulas. Anyway, that's the area of a circle. I'm going to take the derivative. So what I'm saying is the area of that circle is going to change over time. What's causing it to do so? I don't know. Maybe, like I said, it was a rock that got thrown into a lake, and so these concentric circles start to grow. As they grow, so does the area of the surface of the water. So my derivative would be the derivative with respect to time of pi r squared. For this first one, I'll talk through it really slowly, because you're used to dealing with x's and y's, and now we've got a's and t's and r's. What I would suggest you always do is grab any constant, and pi is a constant, and bring it out front. So this would become pi times. Notice I'm not using any prime notation. I told you that was okay with implicit, but I also told you once we go to the word problems, we're going to go back to formal notation. So this would be the derivative with respect to time of r squared. Notice the radius is changing as the area is changing. They are related rates of change. So the pi will hang out front, and my derivative of r squared is equivalent to what we did when we did implicit, and we would do the derivative of y squared. We would say it was 2y, y prime. Well, the derivative of r squared is going to be 2r times, but we're not going to call it r prime. We're going to call it dr dt, the rate that the radius is changing. So when I clean this up, I would say the derivative would be 2 pi r times dr dt. They're called related rates, again, because as the area changes, so does the radius. And the area's rate of change is affected by how fast the radius is changing. That's why there's a dr dt over there. The faster the radius grows, the faster the area of the circle grows. So number 9 is the formula for the volume of a cylinder. You'll need to memorize that by the end of section 2.6, volume of a cylinder. All right, I'm going to take, this one, by the way, is one kids goof up on, and I'll tell you why. It's again, this is implicit differentiation that we're using. It's level 4 of implicit. I said you'll need to be able to apply it to a related rate problem. So when I take the derivative with respect to time of the left, and then the derivative with respect to time of the right, I am going to first pull the constant out front. You don't have to, but it does make it easier. So I'm going to, on the right-hand side, get pi out of the mix. And then I will take the derivative of the rest of the stuff. This is where you have to be careful. This is like, again, the implicit. I've got the derivative with respect to time of a product. So I have to use the product rule, but I have to write it correctly. So we're going to go through that one fairly slowly. I'd have pi times, and then I'm going to put a set of beefies down because I'm going to apply the product rule to this. Very common for kids to skip the product rule on one like this. So let's talk it through. You would do first function, which is r squared, times the derivative of the second with respect to time. So we would have dh dt. Do not call it h prime. By the way, just for the situation, this is a cylinder. And you'll notice that as the radius gets wider, it's going to affect the volume. And as the cylinder gets higher, it will also affect the volume. So that's why they're called related rates. All those changes affect the other ones. If I shrink down the radius, the volume will change, and so will the height. So kind of interesting. So we do first d second with respect to time plus the second function times the derivative of the first with respect to t. So the derivative of r squared would be 2r, but oops, I meant to grab a highlighter and I just crossed it off. Sorry, I meant to highlight that, but I would do 2r times the derivative of the guts. Do not call it r prime, call it dr dt. And that will do it. We'll do a couple more of these and then move along. So this one is Pythagorean theorem. This is used for a lot of them in the real world problems because you're going to have planes flying and trains going and cars going in opposite directions and kites flying. There's a lot of Pythagorean theorem that's going to pop up in the next few days. You will be taking the derivative, like we're going to let go of the hot air balloon and it's going to start rising. As it does, different things are changing. Its height off the ground changes. The angle that it makes with somebody observing it is going to change. So you will be taking the derivative of both sides with respect to time. So when I do the derivative of a squared, I get 2a times the derivative of the guts, which we are now going to call dA dt. Then the derivative of b squared will be 2b times dB dt, and that will equal the derivative of c squared, which will be 2c times dc dt. In this scenario, it will be helpful for you to divide everything through by 2 because you'll be doing the arithmetic without a calculator. Next one, number 11. Isn't this exciting? Number 11 would be the area of a square. As the side of a square grows, so does its area. As the side of a square grows, so does its perimeter. So those are called related rates. The rate that the area changes with respect to time will be equal to the rate that the area formula changes with respect to time. So again, the derivative of anything squared is twice it times the derivative of the guts, which we're going to call ds dt. What this is saying is, as you increase the side of a square, the rate that the area is going to grow will be equal to twice the side length times the rate at which the side is growing. And again, we're not really doing any problems, we're just setting them up. I think I'll skip this guy and I'll skip this guy, but we'll go do number 12. This is formula for surface area of a sphere. As the radius grows, so does the surface area. So they're directly related. So if you had a basketball and you increase the radius and get a bigger ball, obviously the surface area is going to grow too. Our goal is to find the rate at which the surface area is growing. That will be equal to the rate at which its formula, 4 pi r squared, is growing. you can anticipate what I'm going to do. I'm going to yank that 4 pi because it's a constant. I'm going to grab that, throw it out front of my derivative. So I have 4 pi times the derivative with respect to time of the radius squared. This guy right here is implicit differentiation. It just doesn't have the x's and the y's, and we're not going to be using the prime notation. But we're still going to do exactly the same thing you know how to do. You bring the 2 out front, you knock the degree down 1, but then you multiply by the derivative of the guts. It's not y prime now, though. It's the rate that the radius is changing with respect to time. So when I'm done with this one, I end up getting 8 pi r times dr dt. What that means is I can tell you the rate that the surface area of a sphere is changing. Uh-oh, I just clicked on something. I'm good. I can tell you the rate that the surface area is changing if you supply me with the radius of the ball and the rate that that ball's radius is changing. A scenario for that would be when you pump up a ball that's gone flat, a soccer ball or a basketball. There's a certain rate that you're pumping it, and at any given time, the radius is a certain length. I can tell you how fast the surface area is increasing with this new formula. So number 14, we're going to be using a lot as well. This is volume of a cone. So you're going to have a lot of cone problems where either there's water leaking out of a cone or sand being put on a conical pile. There'll be a ton of them. So we're going to find the rate that the volume is changing. Notice what's related to it. As the volume changes, so does the radius and so does the height, and vice versa. If I increase the height of the pile, the radius at any level is going to increase and the volume will increase. They're all tied together or related, and hence the name, related rates. So I'm going to pull the pi thirds out front right off the bat now since we've been doing it for a while, and I'll take the derivative, so that's pi thirds, with respect to time of the variable portion. And all of these are varying. As I increase the radius and the height, the volume will increase, or if water's leaking out of the cone, the radius is going down, the height's going down, and the volume's going down. So I will leave my pi thirds out front. And now this right here is a product rule. That gets missed a lot. It's the product of the radius squared and the height. So be very careful that you set a pair of beefies down and you do your first d second. dh dt, do not call it h prime. We're calling it dh dt. First d second plus second, which is the height, times d first, which would be 2r times dr dt. You can just go ahead and leave that. We're not solving anything today. I'm just getting you used to the calculus notation and how to derive implicitly these geometry formulas. I'll skip 16 and the last one up. By the way, I will be giving you a quiz tomorrow where I choose 5 of these for you to redo on your own. So make sure you're not just copying them down or writing it down without the volume on, although you won't hear me if your volume's not on. So then you'll get them all wrong anyway. You have to have the volume on, or you don't hear me say there's a quiz tomorrow where I pick 5 of them. I'm so tricky that way. I'm what? Oh, I know. Did I put that on the slide? You read ahead? You're amazing. Oh, I've got to finish this video. Shut up. All right. Here we go. If you're watching this and you're in 3rd or 5th hour, I'm doing it in front of my 2nd hour, so they're kind of slowing my roll. All right, one more. So this next formula is the volume. We already did surface area of a sphere. This is volume of a sphere. A sphere is only controlled by its radius. You'll notice there's only one other variable of change in my volume of a sphere formula, where my cone had 2, because a cone has a radius that changes as the height changes, as the volume changes. Again, that's why we call it related rates. We're going to have some problems where you're going to have a car going this way and a car going that way. Well, there's things changing. What else is changing? The distance between the cars, the angle made between the cars. All that stuff changes as time goes by. So on this one, I will take the derivative of the volume will be equal to, anticipate, I'm going to pull the constant non-variable portion out front of my derivative. So I'd have 4 pi thirds times the derivative with respect to time of r cubed. I will use implicit differentiation. So hopefully that's why I was so big on giving you that scale. I told you you're at a level 3 for chapter 2, and that's what I'm testing you on. But once we get to the word problems, we need to be able to do it without x's and y's. It's still the chain rule. It's still implicit. I will still bring the 3 out front. I will still knock the degree down 1, but the derivative of my guts I do not call y prime. I don't call it r prime. That's inconclusive as to what your variable of change is. For the word problems, it's time that's changing and forcing everything. As time goes by, if I am pumping up that basketball, the volume of the air inside is growing as the radius grows. Let's clean this up. This would cancel, and I'd get 4 pi r squared times dr dt. And I think that's enough of them for you to get a hang of. Maybe I'll go do the missing ones like in class sometime. But I wanted to keep this at 20 minutes, and I'm at 21. So you'll have the other video to watch too. There's 2 videos for 2.6a that will be in Schoology. Have a good one. Peace out. Uh-oh. Don't peace out yet.